Hi, my name is Axel Plinge. I'm going to introduce the paper Can You Trust Your Autonomous Car? Interpretable and Verifiably Safe Reinforcement Learning by Lukas Schmidt, Georges Contes, myself and Christopher Mutschler, presented in the 21 IEEE Intelligent Vehicle Symposium, where it also won a Best Paper Award. In this work, the critical application of high-speed lane change is addressed. The goal is to avoid a collision and overtake other cars by means of an advanced driver assistance system. The scenario is depicted here. The agent's red car below drives at a constant speed and wants to reach its target as fast as possible. However, there are two cars in front of it on the highway that are on its way. A faster car in front and a slower one before that. The faster car might overtake the slower one at any time. In order to implement the advanced driver assistance system, we can split the processing pipeline into three steps. First, a perception module processes sensor input from cameras and other systems. This can be implemented by a supervised machine learning model. Its outputs are abstract state information such as speed, position, and distance to the obstacles, meaning the other cars, so-called affordances. Second, the behavioral and motion planning is done. Here, the system described in the paper is implemented by means of reinforcement learning. In order to apply these actions, the car's actuators are controlled, namely the gas, steering, and brakes. In reinforcement learning, an automated agent is trained, shown as the robot here. The agent learns by interacting with an environment over several time steps by applying actions. He gets feedback input in the form of states of the environment and a reward value. The goal is to maximize the total expected future reward. So, the trained controller is a policy mapping from state space to action space. The policy determines the agent's behavior, that is, its way of acting. Since we are using deep reinforcement learning, the policy is learned as a neural network. That means, in effect, a black box that we can neither interpret or verify. This is why we use imitation learning to extract decision trees from the learned policy. As we can see from the example tree, we end up with readable rules that lead to certain actions. What is more, such trees can be automatically verified. We followed the idea from the Viper algorithm, but extended it for safety. So, the method employed here works as follows. We formulate the problem in a simulated environment. We train a neural network policy with safety constraints. From this, we use a novel safety extraction method to get an even safer tree policy. Using automated verification, we can prove that the tree is safe. If we look at the decision trees that was generated with the method, it is quite clear that the policy can be interpreted by a human. It can also be transformed into logical statements. The safety can then be verified by a dedicated formulation in logical constraints and an automated solver. If we look at the evaluation results in terms of performance, we can see that there is almost no loss through safety. The safe versions go as far beyond the other cars as the non-safe baseline. We see here from left to right a baseline neural network policy, a policy trained with safety constraints, policy extracted with the vanilla Viper algorithm, and a policy extracted with our method. If we compare the results in terms of safety, there are clear differences. Note that the randomized bars refer to a simulation where the other cars vary their speed unpredictably. While the baseline crashes in about 6% of the cases, the safe training reduces this to below 1%. The vanilla tree extraction leads again to a larger number of crashes. However, our novel safe Viper approach reduces the number of crashes to almost zero again by producing interpretable and verifiable tree policies. That was a very coarse overview of the paper. Read the paper for getting insight on the actual technical implementation and background. Of course, you can contact us if you have further questions. Bye, see you.